Good morning, everyone. So I'm Marcelo. I'll be presenting to you a few results that I got in my ongoing PhD thesis under the supervision of Walter Blinders. So the motivation of this work is something that we've been discussing the whole conference. That is how star to symmetrical star evolves to a planetary nebula in which we can observe different kinds of morphology. We can already notice in the AP phase some kind of distinguished morphology like ellipticity, in this case of the tau, or spiral structure in this ALMA data from the art tutorials in a sign of a binary. From the radio data we have here two sources, also some kind of structures here. And yesterday we saw at least 3 talks in this subject. So what are the mechanisms that shape these objects? Well, these I took from the APM page, and here I included something more that we discussed during the conference that was remembered by Joey yesterday. And so binarity is something that is always highly discussed. In APN4, it was, I remember at that time that I think that the community was more divided, and in terms of this specific mechanism. And to exemplify that, I'll put here the football game, our traditional football game, where the teams are divided between the binary supporters and the single star supporters. And I believe that now actually the community is more convinced about the binaries. And I also would like to highlight the closing speech by Lone Soccer, where he said we need to find those binaries. Well, of course, we need to observe, to have the observations to support the theory. But then the question is how significant are the other mechanisms? So it is like no one said that maybe the binaries are always requested to support the other mechanisms. So how the other mechanisms are, how significant are the other mechanisms? In the presence of binary, or if they can be alone, in these both scenarios, how significant they are. And then I'm going to steal this quote and say, we need to find those magnetic fields. So, of course, here I'm focusing on magnetic fields because this is the aim of my project. And there are several MHD simulations that investigate the importance of magnetic fields and support that they are indeed relevant to shape this object, but we need the observations to support the models and to better constrain the models. Well, the good news is that the magnetic fields are indeed being observed around the evolved stars. And until a couple of years ago, we would always say that there were very few observations of magnetic fields around evolved stars. But since this paper here from 2012, we cannot say that anymore, because actually they observed polarization in 75% of more than 100 sources. So the magnetic fields are there, they exist, they are common. But we still need to measure the properties of these magnetic fields. So how is the shape of the magnetic field? How is the strength at different distances to the star? So in this project, we selected 5 sources. So it's 1 pre-PM and 4 AGB stars. And we use the VLBA to observe water masers. Here I'm going to remind something that Daniel said on Monday, that the different species of masers are observed at different distances to the star. So if here is the AGB surface, and here is the distance, the SIO masers for near the star, the water masers in the intermediate distance, and the OH masers further away. So everything that I'm going to say here is in this region, in the water maser region. And this is a few tens of AUs. So I'll jump now to the results. This is the first object. It's the only PPN in the sample. We detected 30 major features, and in these masers, so they are located about 40 AU from the central pair. It's a binary. We detected linear polarization in 3 of the features, and you can see here a high dispersion of the direction of the linear polarization. This could, for example, trace the tangent points of a magnetic field, a toroidal magnetic field like this. We also observed circular polarization, and this is this is the spectrum of the Stokes I. This is the spectrum of the Stokes V, and when the Stokes V has this shape, this S shape, this is a sign of circular polarization. And when we have that, we can fit a model, so the blue line is a model, and then we get the strength of the magnetic field. So for this case, we detected 2 circular polarization and the field strength around 50 milligauss. If we extrapolate that to the surface of the star, then of course we need to assume a power law on how is the dependence of the magnetic field along the distance. So if we assume R minus 1, so that's a toroidal field, then we get a magnetic field of 2.5 Gauss in the surface of the star. The second source, this is the HB star, like it's out. We detected 85 major features, and we did not detect linear polarization, but we did detect circular polarization. And this was in these 3 features here, from which gives magnetic fields of between 100 and 200 milligauss. These 2 plots are just a zoom in of these 2 regions here. Again, if we make the exercise of extrapolating that to the surface of the star, we have magnetic fields of between 1 and 4 Gauss if you adopt R minus 1, then it's a bit higher if it's R minus 2. This is a poloidal field, and it's way higher if it's a dipole field. Just a summary of the last 3 sources. So in this one, we detected linear polarization in 9 features that you can see by the direction of the vectors here. It traces the direction of the linear polarization. And we detected circular polarization in 5 features, giving the field strength between 50 and 330 milligauss. And Arctic Virgo also linear polarization in 9 features. You can see the direction of the vectors here. And circular polarization that gives magnetic field strength around 150 milligauss. In APN Lind, we did not detect any masers. So that doesn't mean that we didn't detect polarization. It means that we didn't observe the masers themselves. So some discussion on these results is how is the shape of the magnetic field. So in the ideal case, we need for one given source to observe to measure the magnetic field strength in different positions from the star. So that means using different maser species. But we don't have one object that we have measurements in all the regions. So in the SIO, OH, and water masers. But we are still doing this process. And when I plot here the results of this work, so now I'm talking about only the 3 HB stars, I'm not including the PPN here. So IKETAL, Arctic Virgo, and IRC 6370. So they lie here in this position. So this is the distance to the star, and this is the field strength. And then I looked at in the literature for results from the SIO and OH lasers. So I found for IK tau, result of SIO lasers, it lies here, and only an upper limit for Arthur Virgo here. And I did not find anything for OH lasers, and also nothing for this source here. So then let's see here the IK tau, that is the only one that we really have that is better constrained in terms of observations. So if you try to fit this line here, this is the R-1. It marginally passes through this and this area, so we cannot rule out that. But the R2 and R3 fits better this data. But unfortunately, we cannot conclude which one of this behavior the magnetic field has, or what is the morphology of the field. Another study that we made was to measure the magnetic energy, and now I'm talking about only the water mason region, not extrapolating anything to the surface of the star, so only on the observations. And what we found is that the energy, the magnetic energy, is higher than the kinematic and thermal energy. So from that, I would say that we cannot ignore the magnetic fields as an important mechanism on shaping the planetary magnetism. So I will leave you with the summary. And again, I'm just going to highlight that we cannot, or you should not, ignore the magnetic fields in terms of important mechanisms to shape the global stars. Thank you.
Interestingly, if your points connecting IK tau are extrapolated back and you have 10,000 gauss of the star, we should be able to detect IK tau in X-rays. So that's a very interesting problem, perhaps.
So in several of these stars you had detected many laser features, but the polarization was only detected towards a few.
Sorry?
The polarization signal was detected only towards a few of them.
Yeah.
So is that correlated with, is that a signal to noise issue? That is, the strongest laser features obviously have more signal noise, and therefore you're able to detect the polarization.
Yeah, so we only detect in the strongest lasers, but it's not all the strong lasers that we detect. But let me get here. Okay, so this example. So the size of the circles are stated by the flux of the lasers. So you can see that in these three cases, the circles are quite big. It's impossible to detect in this one series. Now, of course, we still look for it, but it's hopeless. But we could, for example, have detected like this one or this one, and we didn't. So it is also a matter of how strong the laser is.
So that makes me, I'm a little bit less concerned now, because you are generally seeing the lasers towards the strongest features. So it's not that the fact that you're not seeing it towards the laser feature means that there is not a magnetic field there. But it does still raise the concern of you seeing local or global fields.
No, sorry?
Local or global fields.
Okay.
So if you have several strong features and you see the magnetic fields through the polarization signature in one of them or two of them, not in the others, where you should have seen them because the signal noise is good enough, then that points towards that you see more localized phenomena rather than a global field.
That is for sure relevant, but I should also highlight that there is also the projection effect, right? So maybe we have the magnetic field in one position, but not deeper. I don't know if that's the case.
Did I see a question in the back very quickly? Was I imagining that? I know I had a question.
Just the fact that you're getting the field so much stronger even than the kinetic energy points to these being pointing flux dominated. That these are, essentially it's the magnetic field entirely driving the outflows, and not you don't have a mechanism, like, as Eric talked about yesterday, where you're converting the magnetic field into kinetic energies, and that has important consequences. And I think we need to think about that. That when we think about magnetic outflows, we think that we're spinning something up and driving mass out, but in pointing flux dominated that may explain the hollowness of a lot of outflows.
We should move on. Thank you. Laurent Sabine will tell us about